There's another part of the fundamental theorem of calculus. Basically, it's saying if you take the derivative of an integral where your upper limit is a variable, it really is just basically taking that upper limit and plugging it into your function, because your derivative undoes your integral. Well, let's consider a problem first. So let's consider this. Suppose you want to take the derivative of your integral from 1 to x of t squared dt. Well, first of all, you know you'd have to do your integration. Do the inside first. You get a 1/3 t cubed. Evaluate that from x to 1. So you got to go ahead and plug in x minus what you get when you plug in 1. Well, now you'd have to take the derivative of this with respect to x. So you take the derivative of the first part, you get x squared, minus what you get when you take the derivative of your 1/3, which is 0. So in other words, it simplifies down to x squared. So when you're taking the derivative of an integral, where one of your limits is an x, it's basically taking that x, plugging it in here, because your derivative and integral undo each other. So this one here, you take your x, plug it in for each one of these, and we get this. And once again, here's the explanation down below, but it's for the most part what we talked about before. Now, the only difference with this one is, yes, you're still going to go ahead and plug in your x squared for your t cubed and here, but this isn't just a normal x. Now, there's some technicalities that you need to deal with, but for the most part, it just boils down to, if you did use u substitution, you'd have this. And so then you'd want to be going ahead and taking your derivative of this here. In derivative of this, you plug in your x squared, yes, but you got to have this du dx, which is basically the derivative of your upper limit. So for the most part, in a situation like this, you take your x squared, you plug it in for each one of your variables. And then just remember to multiply it by the derivative of that upper limit. So and that's what your 2x is. That's what it boils down to. You don't really have to go through all that u stuff. Just plug in your upper limit for your variable, multiply it by the derivative of your upper limit. And so it simplifies down to this. Well, now we need to talk about total distance traveled and your displacement. There's a difference between total distance traveled and displacement. Displacement is your area from A to B. So it's going to take this. This is below your axis, so it's going to really take it away. Then it's going to add this, which is above your area, or above your axis, which is positive. So it's really kind of like your net distance. Total distance traveled, though, is the area of this added together, plus the area of this, which we're going to count as positive, which is really the absolute value of that. So really, it's the absolute value of this, absolute value of this, absolute value of this, all added together for your total distance traveled. So for this particular problem, we have our velocity given to us by this function in feet per second at time t. So we want to find our displacement. Your displacement from 1 to 5 is going to be just basically your integral from 1 to 5 of your velocity function, what we've been doing before. So you're going to do the integration of each part. And then you're going to evaluate that from your 5 to your 1. So you'll plug in 5, plug in your 1. And you'll just go ahead and add those together then, because you're subtracting a negative. So your total displacement is 32/3 feet to the right. We know it's to the right because it's a positive. And your velocity moving to the right is positive. Now, let's go ahead and take a look at total distance traveled. Total distance traveled, well, this is a graph of our initial function that we had up above. Total distance traveled is really your absolute value. So you got to look at the parts that are above. Well, the parts that are above really would be this here. And then you got to look at the parts that are below, which would be this right here. Well, the part that's above goes from 0 to 4. So we're going to integrate our velocity function. And then we're going to really go ahead and subtract our area here, because our area here is going to be negative because it's below. Well, when you subtract a negative, it's really like adding a positive. So it's taking this area and basically essentially the absolute value of that area. So you have your integral of your function from 1 to 4 minus your integral of your function from 4 to 5, the two different parts that we have up here. So we have your green stuff right here. We have your yellow stuff over here. You just do your integration of each part just like what we were doing before. The first one you'll have to integrate and evaluate it from 4 to 1. Second one you'll have to integrate it, going to be the same thing, but you'll have to evaluate it from 4 to 5. Now, the first one you know should give you a positive area, which it does. Your second one, since you're below the axis, you know should give you a negative area, which it does. We really want to take this area plus this area here, but counting that area there as a positive. Well, that's essentially what we're doing when we're taking the area above and subtracting your negative area, which is below. And so then we end up with 71/6 feet.